Thank you very much, and thank you for inviting me to the session. It's a pleasure to meet with you and share some research from a different continent. Most of you, when you think of Arizona, would not picture this view. So much of Arizona is over 2,000 meters of elevation, and much of our recharge to our aquifers of the region comes from snowmelt. In fact, almost all of it does, because the rains that fall in the summer largely are evaporated and don't recharge our aquifers. Snow hydrology is very different in our arid region. About 70% of the snow that falls sublimates. So there's very small percentage that's available for recharge. So I want to share with you is some work my research group has been doing to better understand recharge processes, improve predictions for models, and to better help us understand the processes of recharge and protect vulnerable areas where recharge might happen. In the area surrounding the Grand Canyon, most of the recharge is ephemeral. It only comes from snowmelt, and it's almost all focused. It only recharges through sinkholes or faults or fractures. And most of the recharge is not within the boundaries of the unit designated as the national park. It's in the adjoining area designated by our national forest lands. The aquifer I'll be largely focusing on today is a very large extensive regional aquifer that's comprised of some Middle Paleozoic limestone units, the Redwall and Muav limestone units, and the water discharges towards the base of these units over 1,000 meters beneath the land surface elevation. This area is unique for karst systems because there are two levels of karst. The primary aquifer here, which has most of the regional springs, was karstified 300 million years ago after it was deposited. And then there were deposition of other sandstones, siltstones, and shale units above it before you have another limestone unit at the cap of it that's also karstified. But there has been a propagation from the sinkholes in the lower unit syndepositionally up through the entire stratigraphic pile, so we have these unique pipes filled with breccia, or coarse broken rock fragments that go through that entire stratigraphic column. Many of them actually, through paleo groundwater flow processes, are also enriched in uranium deposits. And some of the few uranium mines we have left in the US are from these deep breccia pipes in the greater Grand Canyon region. That has led to some serious concerns over the impacts of recharge through those pipes that could potentially contaminate the deep aquifers through mining activities. To understand our regional systems, we have some regional numerical groundwater flow models. The US Geological Survey created a model for all of northern Arizona to try to predict the response of the aquifers to recent and anticipated future recharge. But like most models that we do, it used an equivalent porous media concept for groundwater flow. It was not a conduit or fracture flow model, which would be more appropriate for a karst system. And also, it didn't even use annual estimates of recharge. It used decadal recharge values. What was the average recharge over 10-year long periods of time, which is not very representative of the process of how recharge actually functions. So I want to show you research we've done to better understand that in detail. The other thing that most of you would, when you think of Arizona, you only think of our large saguaro cactuses, but this region, since it's high, cool, and gets snow, has the largest contiguous longleaf ponderosa pine forest in the world. It's a few million hectares of pine forest in this region. Through suppression of fires over the last century and reduction of logging over concerns about endangered species such as the spotted owl and the northern goshawk, the forests have become significantly more dense. They now propagate large catastrophic wildfires, but hydrologically, they have substantially more evapotranspiration from the denser forest stand. We are implementing the largest ever landscape restoration project in the United States to return this entire forest system through mechanical thinning of the dense forest and returning a more natural fire regime. And this aerial photo here gives you an example to show you a piece of forest that has had some mechanical thinning and returning a prescribed fire versus this very clear line back here where you can see regions that are much denser forested areas. We've done some modeling work to understand the hydrological responses from those types of changes from land scale management practices, and based on historic experimental watershed studies in our region and modeling, we believe that there will initially be increases in regional groundwater recharge from doing these types of forest restoration activities. But as we've heard other speakers talk about in the session today, they are quickly overwhelmed by the trends that the climate change models predict for our region of higher temperatures, higher evapotranspiration rates, and lower amounts of precipitation that has prone to greater extremes, both of greater droughts and more extreme wet events. So I want to focus on two different ways we've been trying to improve our recharge estimates in this region. The first one I'll focus on is, so here's the Grand Canyon region, as we call it, the big ditch that flows through here. These blue dots represent all the major springs of the Grand Canyon that come out of that large regional Karst aquifer. Almost all of those springs are connected to large regional faults. This is a geologic map of the area where the main water supply for Grand Canyon National Park, Roaring Springs, discharges. And it's difficult for me to explain the concept of scale and space of time in this region because maps make everything look convenient. But for us to access many of these field sites requires 3 to 5 day backpack trips through commonly over 45 degrees Celsius weather. So it's a very challenging field condition to study and work in. So this is a student and I on a recent expedition last year. It took 4 days to get to this spring. And this is a common type of spring in this region. It's just to give you an idea for scale, each of these little green blobs right here is a 20-meter tall cottonwood tree. So these springs gush out of cliff faces that extend into caves that go kilometers back in to the rock walls beyond the canyon. Many of you well, he's not a great picture of him, but this is Gary Schindle's son, Graham Schindle, who did a master's thesis with me and finished up a year ago. Graham focused his thesis work on the water supply spring for Grand Canyon National Park, which is shown here. Again, to give you a concept for scale, these are mature cottonwood trees about 20 meters tall on this cliff face, to give you an idea of the scale here. So the Grand Canyon National Park is the second largest karst park in our national park system. Only the Everglades has more area of karst. There are over 600 known caves in Grand Canyon National Park. There are at least 2 caves now that have been mapped over 30 kilometers. And they will all be much larger, it's just they're very difficult to access and challenging to explore and understand. Roaring Springs has a bit longer history to it. Here's a cave map done by Peter Huntoon back in the 1960s for his doctoral dissertation at the University of Arizona. All of our monitoring equipment we've placed about 400 meters inside the cave entrance because the cave entrances disperse before they hit the rim and the flow disperses, so they're all a single spot within there. What Graham did was his thesis, he was the first one to deploy long-term monitoring equipment to look at the natural tracers of temperature in this system. And he was fortunate in the year of his thesis that we captured an unusually strong and wet summer monsoon season in our region. It's rare, and we've never observed it in 30 years, where we get a summer rainstorm strong enough that we get recharge to this aquifer that's over 1,000 meters deep. And we had about 8 straight days of heavy rainfall in late August this year, and we saw a temperature pulse through the spring over 1,000 meters down and tens of kilometers away horizontally within 2 days. So even though this is a deep karst system dissected by some non-karst units in the middle, there is still a very quick response to certain flow events in this region, which is counterintuitive for what most people think. That's a concern for the water manager to be concerned about protecting the source areas for that spring system. And we don't know what they are. So this is what we're trying to do now. Some of you may have met Dr. Benjamin Tobin. He's now the hydrologist, cave resource specialist for Grand Canyon National Park. And he's begun introducing dyes to the rim of the park. These were ones we put in 2 years ago. And what we've done is we backpack into all the remote springs in the park and put out these passive charcoal receptors. And we're just doing some qualitative dye tracer studies now to figure out which sinkholes connect to which sources. So here's Grand Canyon National Park. These green dots are the springs. These purple dots represent the 2,000 sinkholes that exist on the Kaibab Plateau that are potential recharge areas. So we currently have absolutely no idea which of these sinkholes connect to which of these springs. There's no geophysical data, there are no bores, there are no other subsurface data that we can use to, of course, understand these systems. So this year, we introduced 2 other dyes within the park boundaries to these systems. And just yesterday, I got new data from Gary Schindel at the lab. And remarkably surprising for us, a dye introduced at this spring purposefully that we thought would flow to the water supply spring, Roaring Springs in the park, flowed tens of kilometers this way and came out at these 4 springs in the park. So that's our dye tracer studies, and I gave you some reasons for them. But we do get recharge that is not ephemeral and focused. So we've been implementing other studies to try to understand the role that distributed recharge has on our landscapes and the role that forest restoration plays in that. And we've done that by implementing a technique called chloride mass balance to get recharge. Water that evaporates from the ocean includes small amounts of chloride in the precipitation. As those air masses move in our region from the Pacific Ocean over western North America, the precipitation falls out with some chloride in it. We then trace to do a balance on the amount of chloride that runs off through ephemeral streams. It passes through soil water and the mass that's in precipitation. And by the difference, we can determine how much water recharges. We've deployed that on some field sites in our region. This was our trusty field assistant, Carlos. He was Vaden's main field assistant at this field site. And we also implemented this tracer study under different types of forest treatment practices. So we had some plots where the forest has been thinned mechanically. The trees have been cut. We had some channel sites, some park-like meadows, and some unthinned sites. And so it's a steady state technique, relies on natural chloride from precipitation, and we do a mass balance approach to get the answers. We found that this technique, we're just finished, actually next week when I get home, I'm doing our last month of sampling over this 2-year study because all of my students are graduated. And largely I'm going to show you the results from the first year of the study, which we think showed significantly good progress. And in our region, only about 1 to 4% of total precipitation recharges the aquifer, very small amounts. So you'll see the amounts here are only a few millimeters up to a few tens of millimeters. So it's very small amounts of recharge in our region. And we find we've been doing the chloride mass balance approach on a monthly sampling scheme. So we've been able to determine monthly recharge, more detail than annual recharge. So just to summarize here for you, recharge, as I showed you in our region through the dye tracer studies, can be focused and ephemeral through sinkholes. It's not generally uniformly distributed, although with the chloride mass balance, we see that there are some very small amounts of recharge that are distributed airily. We've been surprised by the directions that the dyes are currently traveling right now. As you might imagine, it's quite a logistical challenge to get a national park unit's water supply and the adjoining forest unit. It took us 2 years to get the permits to introduce these dyes in these systems. And then I've showed you, we think there's some promise, and I'd encourage you, if you're interested, we'd be happy to share with you the techniques for the chloride mass balance method, if you might find that might be interesting for some of your study sites. And we do find that the slow recharge is also important for this deep karst system. So this project wouldn't be possible without support from some of our major water providers, my postdoc, and other students and collaborators. So thank you.